getting to the failure theory. So what we have done so far is we did FPD, and then we did shear force diagram, and then we did bending moment diagram. Okay, what the outcome of this was a shear force V and moment M. Now, this V and M will help us to compute normal and shear stress, uh, which is sigma x, sigma y, tau xy, and this tau xy, sigma x, sigma y, then went to the Mohr circle or the transformation of stresses. It actually will give us the maximum stress, sigma A, sigma B, tau A, tau B, and then that will actually go and feed into design based on, these are principal stresses, so design based on principal stresses. So an example for principal stress is maximum shear stress, a very commonly used criteria. Maximum shear stress. If you've done any ANSYS calculation, you'll see that it actually plots maximum shear stress. So when we talk about maximum shear stress, we're really talking about this value, sigma 1 minus sigma 3 divided by 2. We computed this value earlier in the Mohr circle. So what we have done so far, we have done this, we computed Mohr circle, and this is what we're going to do next. We are going to compute how we can use the V and M to get the normal stresses sigma x, sigma y, and tau xy. And this will come later. This is where we can actually figure out if something is going to fail or not. Okay. So let's get started with normal and shear stresses in beams. Okay. Now there's a little bit of theory here before we actually get to problem solving. And some of this will be a review. It's not new. This is something you've covered in strength of material. I'll quickly run through some of the basics. So that way you are aware of what's going on and sort of get you to speed if you've forgotten strength of materials. And from there we will actually solve problems, and that will help us to advance to the next part, which is design. So if you think of a beam, and if you apply a moment M, it will clearly bend in the way it's shown, and it's clear that the top part is going to be compressed. It's compressed because you can see that the distance is reduced and the bottom half is elongated. So if the top part is compressed and the bottom part is elongated, there is a line which is not stretched or compressed. It has to be, right? Because if one part is decreasing in length, another part is increasing in length, there should be a midpoint which is not unchanged. So that unchanged point is called a neutral axis. Sorry. So this should be neutral axis. Okay, so region above the neutral axis compress, and region below the neutral axis. Now this the statement here is to be taken with only this figure. Now you could have a scenario where this M is reversed and the beam will bend this way, in which case clearly the bottom part is under compression, the top part is under tension. So this statement which I've put over here only applies to this figure, so be careful when you use it. Yeah, here I've said it. If M is reversed, then we'll have the region to switch. So that is actually, let me move it here. This is this case. Okay. Now let's get to some theory. What I'm showing you here is the unstretched beam. So there's no force acting. It's going to be straight. Nothing will change. If you apply a moment M, it's going to deform in the shape shown earlier. Top part will compress, bottom part will stretch. And if you take this and you connect, you basically extend this line here, the green line, that dashed line, it will join at a point. So it's actually an arc of a circle of radius r. With this radius r is used to denote the distance from the meeting point of those two lines, the green lines, with the neutral axis. Okay. Now, strain, definition of strain was change in length to the original length. So we'll find a strain in some beam element C prime d prime at some distance y from the neutral axis. So C prime d prime minus CD divided by CD. So this is just the definition of strain. The change in length, which is the numerator, divided by the original length. In this case, the original length is just CD. That remains unchanged. That's the neutral axis. So you can use this formula, which basically gives you the arc length given the radius of the circle, to compute C prime d prime. It's going to be, well, CD is easy, right? CD is going to be uh, r times theta. So this arc length, this arc, so let me put this arc length is just r times theta, where r is the radius. This is just from how you can compute the arc length of a circle. And the same thing can be done for C prime d prime, except the radius now is going to be r plus y. So here is strain formula reduces to y divided by r. It's non-dimensional. Okay, now once we get the strain, we want to compute the stress. The definition of stress is that stress is E times strain, where E is the Young's modulus. So strain from the previous page was y divided by r, and so stress is E y divided by r. If you want to draw the stress, one way of drawing the stress is with these arrows. So on the neutral axis, which is this point here, use a different color for this. We have y equals to 0, and so stress is 0, right? If you put y equals 0 here in this formula, it is simply 0. And then if you put y equals y max, this is the end of the beam, then sigma will be sigma max, right? So that's pretty much what is shown here. The red arrow here on the bottommost part is maximum. Similarly here, y is y min, and so sigma will be sigma min. Okay, note that y is measured from the neutral axis. So you can see that this part is in tension, this part is in compression. This is the stress profile. It's always 0 on the neutral axis, and it's 0 understandably because CD is not stretched, right? So strain is 0, so stress is 0, and then it increases linearly with linearly as you go far away from the neutral axis. Okay, so that's again shown that this, what I said, is exactly illustrated, but it's stated here clearly. Is proportional distance, so sigma is proportional to y, and as this is something I showed earlier, compressive, no stress, and tensile stress. Okay. Now, once we get the stress, we want to somehow equate it to, eventually we'll come to a formula for the neutral axis. We want to find the neutral axis. Now, it looks like the neutral axis is always in the middle, but what does middle really mean? This beam is nice and rectangular. What if the beam was something like this? Right? What is the middle? Is the middle here or it's here? We don't know. So how do we compute the neutral axis? So here's a way to compute the neutral axis, or the position at which is unchanged. So what we'll do is we'll find a net force at section C prime D prime. So the force is simply stress times area. So that's the definition of force, right? Stress is force divided by area. So we move the stress, the area around, and we get force. Now, this is the force on a small element, some small element here. In order to compute the complete force, we need to integrate force across the whole area. So df, integral of df. So we can write df as sigma times delta A, but sigma, the formula for sigma is simply E Young's modulus times y divided by r. So we put that. And one thing to notice is that this is subjected to pure bending, right? What we did was we applied an M. We did not apply a force. So you can go back and see. This is purely a result of a moment M. There is no force. There's no force, absolutely no force applied on this beam. So what we can say is that the net force is actually 0. It's a purely bending moment. And so if force is 0, then integral y dA, this thing, is 0. But centroid of a shape is also given by the formula which is similar to this. It's actually integral y dA divided by dA, which is saying that the, the, the denominator is always positive because the integral of area is just the total area, it's positive, which means that the numerator has to be zero. And if the numerator has to be zero, it has to be the centroid. So centroid and the neutral axis are synonymous. If you want to find the neutral axis, you just find the centroid. And that calculation is very straightforward. You need to find to take the areas, find the center of each area, and then apply a centroid formula, which you probably have learned before in probably in some math class. Yeah, so we'll apply this formula a little bit later, but just remember that centroid, we're after the centroid of the shape. So finding the centroid of this shape is fairly straightforward. You will actually break this down into two shapes like this, and then find the centroid of this and centroid of that, and then you can just do some use this formula to figure that out. We'll do that in just a bit. Now let's take another uh, find another formula for moment, and then we can proceed with some problems. So moment is, this is just taking the formula a step further. We've computed the net force. Now take the force and multiply with the distance from the neutral axis. So this is y. So dF times y. Remember that this force is assumed to be acting this way. So this force and this y are 90 degrees. So it's dF times y. You take the integral. So substitute f df as sigma dy dA, and sigma for this substitute as ey divided by r, and you can pull out e and r because that's a constant, and you're left with y squared dA. So it turns out that there's a very well-known formula for y squared dA. It's called the planar moment of inertia. Okay, again something which you might have done in a calculus class. This I is the planar moment of inertia, and there are tables which gives you this formula. So what we have figured out here is this formula for the moment is ei times r, where I is the planar moment of inertia, r is that radius, the radius about which that the beam will curve against, and then sigma is ey divided by. So we derive this, we derive this. This is just putting both these formulas together. So m divided by r is e divided by r. The same thing you can see here is sigma divided by y. So this is combining these two formulas into one single form. So this is the formula you want to remember or use it for calculation. So let's see how this formula is used next. Okay. So problem one. Okay. So we've covered a lot of theory, and hopefully these problems will make it clear on how to use the formulas. Okay, so a steel bar of 0.8 times 2.5 inch is subject to a moment m as shown. Find m that causes the bar to yield, given sigma yield is 36 ksi. What it means is you're given uh, sigma yield. So it's also actually sy, which we have seen in the last class. It's the stress at which things will become non-linear. So sigma y, maybe I should have said sy. So sy is 36 ksi. If you remember last class, we had this curve, and then I said this is sy when things start becoming non-linear, and you really want to not go to SU. SU is like ultimate strength. You want to design based on this. So even if you are wrong on this, you have some leeway for this material to still withstand some load before it fails. So you're given SY is 36 ksi. You are asked to find M. Okay, you know, find M such that you hit this point. That's the question. So how do we do this? Well, first of all, what formulas do we know? We know we somehow need to get M. So the only formula I can think is the last one we wrote down. M divided by equals E divided by R equals sigma divided by Y. I think that's the formula. That's the only formula involving M. Okay, so in this case, I think we don't need this part. We only need the first part, because E is not given. So M equals sigma I divided by 1. Now it's said we have to find the maximum moment. So if M is max, then sigma would be max. Sigma max is Sy. I have to figure out, and then Y would be Y max. Okay, and Y max, we know it occurs. So this is the axis. We know we have to measure Y from here. So Y is max. The value of max Y is going to be, so measure from here, go to the maximum. So it's going to be half of 2.5, 1.25 inch. Okay, Sy is given to us. We need to find the moment of inertia, planar moment of inertia. So planar moment of inertia is given by y square dA. Okay, turns out that for this cross section there is a table. Okay, this is something which I need to provide to you. There is a, let me see if I can find it. There is an appendix which I will provide to you, and you can actually use that appendix to write many of these things. Maybe I have not posted it yet. Let me just find it for you, and just show you where it is. But I'll post this on Canvas. I'm going to quickly find it on my computer. Okay, so this actually is in Appendix A18. Document. This is in the end of the book. It has, there are 25, there are 34 sections in this. We are looking at A18, geometric properties. Let me blow it up. Let's go to A18. I think it's page 1044. Okay, here it is. So this is giving you moment of inertia, planar moment of inertia for certain sections. So y square dA is what we're after. Iy, so we want y square dA. Okay, so this is the cross section. We are in rectangular cross section. So for this one, the Ix is y square dA. So it's bh cube divided by 12. So b is the base, it is the height. So you do bh cube divided by 12. So if you look at this and compare it against this, what you're trying to do here is bh cube. B is 0.8, h is 2.5. So it's 1 divided by 12 times 0.8 times 2.5 cube. I'll write it down just a bit, but you're looking essentially for, where is it? Here. It's looking for this formula. So it is b h cube divided by 12. B in this case is 0.8. H cube is 2.5 cube divided by 12. Okay, so finally, when we solve this, we have M max equals SY 36 KSI 0.8 times 2.5 cube divided by 12 divided by Y max. So it's 1.25. It comes out to be M max equals 30 kip inch. So that's the unit in foot FPS. 30 kip inch. Okay. Okay. Next, let's move to a slightly harder problem. A rectangular tube has an ultimate strength of 60 KSI. So here we're given the ultimate strength, and that is 60 KSI. 60 KSI. And dimensions are shown. Find A, bending moment, such that factor of safety is 3, and radius of curvature. So this is part A. Part B is radius of curvature So radius of curvature is actually 1 divided by r. So r is the radius, and radius of curvature is the inverse of that, is unknown. We are given E is 10.6 times 10 raised to 6 psi. Okay. Okay, so let's see how to solve this. Okay, so the only formula which I can think of which can put all this together is probably the one I wrote down last, the last formula I wrote down in the notes, which summarized everything. M divided by R is E divided by M divided by R is E divided by R divided equals Y divided by uh, E divided by Y, sigma divided by Y. And this, what we'll do is, just to save time, let's just make this max, which holds for any values provided you take consistent values, so all max. Okay, so what's unknown is M. What's unknown here is 1 divided by R, so in a way R is unknown, and the remaining things we need to figure out. Okay, so sigma max, okay, now sigma max, well, SU, as you remember, it's basically that point, and this is SY. So in this case, what they want to do is, uh, you could take SU and use that to figure out a design criteria, or test it based on that. But what they want to do is they want to wrap around a factor of safety of 3. So even though SU is 60, they don't want you to use 60. They want you to use a SU divided by 3. So that will actually reduce. So if you so sigma max. So the definition of N is SU. Okay, now some people use SY, some people use SU. That's just a designer's choice. So in this case, sigma max will be SU divided by N. So it'll be 60 divided by 3. So that'll be 20. In other words, what it's saying is that what you're going to do here is you're going to take SU and reduce it by a factor of 3. So it'll actually be, maybe it's close to SY. Okay, so I mean, that's maybe true. I don't know the actual SY in this particular case, but that's a way to drop it down. So design is based on SU and not based on SY. That's absolutely fine. The second thing is we can find Y max. This is also very simple. For a beam, the max always occurs from the neutral axis. In this case, even though this is not a pure rectangle, you can see that it is two rectangles put together. It's clear the neutral axis has to be passed through the center because it's a symmetric geometry. Right? So Y max is going to be always from neutral axis. We measure the Y. So this is going to be Y max. So Y max, you can see it's 5 divided by 2. Okay, so let's see what we have so far. We have got uh, E given to us, sigma max given to us, Y max given to us. We need to compute I though. This is unknown. Once we get I, it should be very easy to solve for the remaining things. So let's compute I. Now, first thing you want to do when you think of I is think of A18. Go to A18. Let's go to A18 and see if they've given the inertia for this particular geometry. So here is A18. We can see that it has they have inertia for rectangular cross section, a circular cross section, an annulus, hollow circle, a triangle in various forms, quarter circles, and then it goes to three dimensions, right? It is not the appendix does not have a value for the inertia for the geometry we have in mind. But what we can do is we can actually use the rectangle to figure out the inertia of a solid with a circular or sorry, a rectangular hole. So what we'll do is we'll use this in order to do that. Let's see how to do that. So here is how we'll compute the inertia of a hollow rectangular section. So what we have is a cross section which looks like this. Okay, I'm going to draw it a little bit exaggerated. Let's use a different color. Okay, clearly it's not like this, but I just exaggerate this. Now this is what we want. And of course, it is actually uh, it's hollow here, right? So it is basically this. Let me paint it. It's just blue. So this is what the section looks like. It's hollow inside. Okay, so what I can do here is I can actually compose this in the following way. I take the rectangle and I take the inner rectangle. Let's use green. So this rectangle, and I'm assuming it to be a solid rectangle. And then we'll take a solid smaller rectangle. And if I take these two and subtract the second from the first, I should get this geometry. So if I want to find the inertia of this, then I just find the inertia of this first one, the bigger rectangle, minus inertia of the second rectangle. This is known as what is known as superposition principle. It does hold for these geometries, um, and you can just use it. So the inertia for I1 is going to be, we had done this earlier, it is bh cubed divided by 12, b being this, h being the height. So if there's b1 h1 and b2 h2, then we can find the inertias. So we go back to this figure, we see that b is 3.25, h is 5, so 1/12, b is 3.25, h is 5 cube, minus, let's go back here and try to figure out what is the b and h for the smaller rectangular. So it's 3.25 and I have to subtract t and t from either sides, and same for 5, I need to subtract t and t. So what I'll do is I'll just write it down as so t is given as 0.25. Okay, I'm going to make some space here. Okay, and then minus 112, 3.25 minus, I'm just going to subtract. So 2 times 0.25 is 0.5. And then 5 minus 0.5 cube. Okay, so this is 2.75. This is 4.5. Okay, so the answer is I equals, so if you do the math, it comes out to 12.97 inch raised to 4. Okay, so this is, the next part is straightforward. Now we have computed I, this is known, this is known, and so we just have to plug in the formulas. So M max is sigma max I divided by Y max. Sigma max is 20, I is 12.97, and Y max is 2.5. So from this we get M max equals 103.8 K pinch, and then we have to compute the 1 divided by R, or rather let's actually figure out R. So curvature is 1 divided by R, but let's just figure out R. So R is E Y max divided by sigma. Sigma max. So E is 10.6 times 10 raised to 6. Young's modulus is a big value. Y max is 2.5. Sigma max is 20. And since it's KSI, I'm going to put 10 raised to 3. Okay, now what you will get is 110 feet. Okay. Uh, and curvature is 1 divided by R is, do this calculation, 0.009. So this is one answer. Okay. But I want you to think about this thing. What does this really mean? What does it mean for the radius to be 110 feet? It's saying that if you bend this, so if you, in this case, it's basically this section. Draw it properly. So it's basically a rectangular section. It's saying that if you bend this, it will clearly become like this. And then this radius is going to be 110 feet. Okay, that's so a human being is 6 feet, and this is 110 feet. So at 60, what 20 times, at least 20 times the human height, maybe a 4 or 5 feet building, and that makes sense because these beams don't bend too much. So if the radius is large, it's a good sign. This is really good. If it was very squishy, then you would see that it will bend to a great extent. This radius will be very small. You don't want the beam to bend that much. So R great is a good sign. It's not going to bend too much. In fact, one of the properties of any, if you see physically, if you see that something is bending too much and if the radius is short, you'll be very nervous. But the fact that it is not bending that much, bends by 110, the radius is 110, it's a good sign. So this is uh, I would say, looks safe to me. So there's some things you want to care about when you are have these numbers. Don't just see an answer, don't buy it. You have to think about it. Does it make sense or not? Especially when values are too high or too low. Okay, I completely forgot. I actually had these appendices for the A18 in this book, in this section. So if you wanted them here, but I'll post that appendix for you for a reference because we'll be using it a bit. Okay, so let's get to the next problem. And maybe we can take a break after this. It's pretty intense. So let's solve this and then take a break. So a beam is acted upon by moment m. This is 3 kilonewton meter. Determine the maximum tensile and compressive stress. So sigma max and sigma min. Okay, those are the unknowns. Okay, now the thing which makes this problem slightly interesting, but more harder than previous problem is that the section is not uniform. There's no symmetry. Because it's not symmetric, you don't know where the neutral axes are. It could be here, here. So we need to first find the neutral axis, and then our calculations will go from there. Okay, so first step is to find the neutral axis. So we'll compute neutral axis. Okay, so once we compute the neutral axis, let's say that this section will look something like this. Okay, and maybe there's a moment like this. So it'll bend, and the neutral axis perhaps Okay, I'm just making up something here. I'd have to do the exact calculation. Maybe the neutral axis is right this plane. This plane is the neutral axis. If it's bending like this, uh, hold on, I think I got the sign wrong here. So if you look at this, this should be, yeah, given the direction, I got it, I wrote it exactly wrong. So M is the other way. So M is this way. Okay, so if you compress this way, it's clearly going to bend something like this. So the bottom part is going to be under compression. So this part compressed, this part tension, right? Because the shape, it's going to be like this, just based on this moment. Now, once we find the neutral axis, to compute the maximum distance, it's going to be this distance for the tensile and this distance for. So, given this, what we can do is m divided by I, going back to this formula, m divided by, sorry, here it is, m divided by I is sigma divided by y. So, what we can do is we can compute m divided by sigma tensile divided by y tensile. So, this will be this distance. So, the distance from this to, we use a different color for this. So the distance from the maximum, the height from the neutral axis, let's call that yt, and then this distance from the bottom one all the way to the neutral is yc. So that would be sigma c yc. Okay, so yc and yt are computed once you know the neutral axis. Sigma c and sigma t are unknown, so I'll put a question mark. M is known, it's given as 3. This will be computed from neutral axis, and this will follow. If you know the neutral axis, we can then find I, because I depends on planar moment of inertia, depends on where exactly the centroid is. Okay, so two steps. This is based on neutral axis, and then this I after computing neutral axis. So you cannot do I computation unless you know the neutral axis. So we are sort of stuck doing the neutral axis first. So we'll do this calculation first and this calculation second. So let's do that. Okay, here we go. Let's do the first calculation, neutral axis. For that, I need to redraw the figure as it is, like this. Okay, now when I want to compute the neutral axis, um, I need to use the centroid formula, and the centroid formula is y bar equals summation y a divided by summation a. So what you do is you split this into smaller sections whose area and centroid are known. So I could think of splitting this into, so this is one way of splitting it. This is not the only way to split it. If you want to split this in another way, and this is what I would not do here because I'll tell you in just a bit, you could split it this way. You could split it this fashion. So you'll have this, this, and this, and you can do the same calculation. The reason why I'm not doing this part is because you need to split this into 3 sections, which means your calculations are, you're going to add another calculation. Here you have to only consider areas of 2 sections. So I wouldn't recommend this because it's going to waste time. So let's stick with this. Of course, you can also split into many, many more parts, but you want to stick to the smallest number of parts. Okay, so we have this and we want to find the neutral axis. For that, what we need to do is we need to first lay down the dimensions. So let me lay down the dimensions of this from the figure. So we have 30, 40, 20, and 90. Okay, let's see if I can remember that. 30, 40, and then 20, and then 90. Some space for this. Okay, so now what we'll do is, just to make it less clutter, I'm going to redraw this. Okay, I will start off assuming, so if you want to find the centroid, you want to assume some axis. Okay, you can choose axis anywhere you want. For a symmetric profile, you're best off choosing an axis such that at least one of this, well, I just choose it here so that there's a symmetry. It's symmetric about the y-axis, so the right side and left side are the same. So it's symmetric about this line. So I'm just going to use the middle plane as the line about which I'm going to draw the origin. Now you could put this over here too. There's no problem in doing this, or you could put it here. It's really up to you. I'm just decided to go with uh, the top section, top half of the T section. Okay, so this is the origin, and now let's do is find the centroid of this. This is the centroid, and that's the centroid. This is very obvious, right? It's the center of the geometry. What I need to do is I need to find the distance of this point from the origin. So in this case, the distance is going to be this much. So you can see it's 20 divided by 2, half of 20, so it's 10. And then I also need the distance from here. So we know that this midpoint is approximately at 20 from the top, and then we need to add another 20 because the origin is up there. So 20 plus 20 is 40. Okay, um, and that's it. So let's write down this formula now. It's YDA. So this is going to split into two geometries. So let's call this 1 and call this one 2. So Y1 A1 plus Y2 A2 divided by A1 plus A2, where A is the area and Y is the distance from the origin. So for Y1, this is 1, we wrote 10. And you know what, to make it consistent, we have assumed upwards to be positive. So I need to make it minus 10. The distance of this point from the origin is minus 10, right? Times A1. So A1 is this area. So it's 20 times 90 times 90. This is the area. Plus this distance is minus 40. And then the area is 30 times 40 divided by the total area. So it's 20 times 90 for area 1 and 30 times 40 for area 2. Okay, so plugging in the values, you will see that it comes out to be minus 22. And I think I'm using, is it millimeters? Okay, it comes out to be 22 millimeters. So now we can zoom in and figure out exactly where the centroid is. The centroid is, so this is 0 and this is 20. So it looks like the centroid is right sitting just below this T section. So it should be here. This is the neutral axis. It's at a distance of minus 22 millimeters. So from the top. Okay, so that's the key. So that's the first part. We've got y, which means we can now find compute yt and yc. Yt and yc are just the distance from the neutral axis. So we can write that down here. So yt, the top part, so this is the distance from the neutral axis to the top half, and you can see that is clearly 22 millimeters. Okay, 22. And then yc is the distance from the neutral axis to the bottom, this one. So it's going to be 40 minus 2, I think. So it's 38 millimeters. Okay. Note that this is the distance from the neutral axis, and it is not the distance from the origin. So these distances are distance from neutral axis. That's very important. Okay, so we've got the first part. After doing all this, we've got yt and yc. Now let's compute I, and then we should be ready to solve the problem, get the final answer. So how do we compute I? Now for I, this is going to be the inertia about the neutral axis, and that's what makes it kind of involved. So let me redraw the T section. Okay, uh, the neutral axis we figured out was here. So now what I need to do is I need to compute the inertia, and then we know that from this table A18 we don't have the inertia for any of the T section, so we need to compute it from scratch. So I'm going to compose this of two rectangular sections. Again, this choice is arbitrary. If you want, you can split into more parts, but try to stick to the minimum number of areas, which gives you the which you're going to which you're able to split. So here is two of those, is the top and bottom, and clearly I claim that this I is going to be I1 plus I2. It's a matter of figuring those out, and both have to be done about this axis. Okay, the axis will remain same, so this you can say is equal to this plus this. Okay, now let's compute this. So what we need here is um, the distance of the center of this from the neutral axis, and that is easy to find, this distance. You know what, let me put on all the dimensions here, 40, 20, 30. So 40, 20, 90, and I think 30. Okay, so this distance now you can see this is 2 millimeters. So it's 2 plus half of 20, so it's 12. Okay, I think that's right. And this distance is going to be, wait, it's going to be 20. This is minus 2, so it looks like it's 18. Okay, with that we can compute I1. Now for I1, again, if you look here, the formula is BH cubed divided by 12. I'll zoom it a little bit. It's BH cubed. So B is base, H is height. So what you need to do is you need to first find the I1 about its own axis. So I1 would be B for this one is 90 times H cube, height is 20, divided by 12. So that's the moment of inertia, oh, sorry, planar moment of inertia about its centroid. But the problem here is that the centroid for the composite figure is about the green line. It's not about its centroid. So we need to find the inertia about the green line. In order to do that, we use what is known as a parallel axis theorem, which says that if you want to find the inertia about another line, like the green one, all you do is take the area of this section, so 90 times 20, and then multiply it with the distance square, the distance of the neutral axis from the centroid squared. So in this case, the distance of the neutral axis, green line from the dot, is 12. You square it. So this will be I1. Okay, now I want to park this somewhere else because I think it's going to be very confusing. So I'm going to write I1 as this. For I2, use the same method. So I2 would be base. The base is 30. The height of the second one is 40. So you cube that, divided by 12. plus area, which is going to be 30 times 40. Yeah, I need to be generous with space. I'm going to move this. Okay. So then we have area 30 times 40 times the distance of the green line from the dot from the centroid. So it's 18. So it's 18 square. Okay. So I'm going to take that and move it down. Okay. So we just compute that. It's fairly straightforward now. To get I is I1 plus I2 equals 8.68 8.68 times 10 raised to negative 7 meter raised to 4. Okay. So now we have, in this case, computed the second part too. So this is known. So it's just a matter of using the formula. So here we go. So putting it all together. So let's find tensile stress. So that would be m divided by r equals sigma t divided by yt. M is 3 times 10 raised to 3. I we just computed 8.68 times 10 raised to negative 7. Sigma t is unknown, and yt is, we wrote it down earlier from the neutral axis. So this gives sigma t equals 76 megapascals. So that's answer 1. And then compressive stress. For that, the same formula, but replace sigma t with sigma c. So 3 times 10 raised to 3 divided by 8.68 times 10 raised to negative 7 sigma c divided by 38 10 raised to negative 3. That's just to convert the millimeters to meters. And so sigma c comes out to be 131.3 megapascals. Yeah, so here is where it's kind of interesting, which is if you see this beam, we know that the top part is in tension. This is the neutral axis. This is tension. This is compression. You notice that the tension is 76, but the compressive force is 131, and that's because the neutral axis is actually skewed towards the top. So this is actually wrong. Should be something like this. So this is the axis are like this, right? This is 20, and this is 40. So the axis, since the axes are closer towards the T, what happens is the maximum compressive stress is actually down. Okay, which means that if you're trying to think about failure, this point will probably have a high chance of failure versus this point, which is going to have less stress.